All right, we'll get started, and we'll pretend like everything in the world is okay, and we'll we'll talk about Markov chains. So, okay, so we today I want to introduce kind of the idea of what's called a limiting distribution. This is the well, let's talk about this. Okay. All right. So on Monday, we talked about some Markov chains, and we said, you know, here's like a simple Markov chain. This is a two-state Markov chain, and the two states are 0 and 1. So that's the state space. So the Markov chain can either be a 0 or it can be a 1, and it's got this transition matrix. It goes if it's at 0, it can go back to 0, and that happens 80% of the time. And 20% of the time, it will transition from 0 to state 1, state 0 to state 1. And then if it's at state 1, it will switch back to 0 60% of the time, and it will stay at state 1 40% of the time. Okay, so what we want to see is what will happen to the chain if we run it for a long time. I wrote 1,000. I think I did like 100,000 actually. So we'll start the chain. We'll start it at 0, and then let's just see what happens. Okay, there is a cool website, and so this is kind of an illustration of what happens to the chain here. Okay, so I've already plugged into the website, kind of the transition probability spectrum. Where did it go? Okay, and so this is what we have here: 0.8, 0.2, 0.6, and 0.4. And you can see, I'm going to crank the speed up a lot. Okay, you can see that it goes to A a lot. Sometimes it switches from A to B, and then sometimes it will stay at B. But a lot of times, 80% of the time, from A it goes back to A, and then it goes to B, and then back to A. Sometimes it goes B and does a loop. And so if you're keeping track, what is it generating? Here it's going A, B, A, B, 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 A. So it's generating a lot of A's and a few B's every now and then, okay? And the question is, what's going to happen in the long run? How many A's and how many B's are we going to get? So I just wrote up a little bit of code that will run the Markov chain, okay? So so create the matrix, the transition probability matrix, okay? 0.8, 0.2 for the first row, 0.6, 0.4 for the second row, okay? And then I guess we'll do this 100,000 times. And I'm going to start off at 0, and then everything after that is blank, okay? And then starting at the next position, what we're going to do is we're going to look at the previous state, okay? So we're going to look at state I minus 1, okay? And that's either going to be a 0 or a 1. So if the previous state was a 0, we're going to use row is going to be 1. So this will be a 0, and then we add a 1. So row will be 1. And if the previous state was a 1, then our row will be 2. Okay, so this is just to tell us which row am I going to use. Am I going to use row 1 or row 2? And if the previous state was a 0, we use row 1. And if the previous state was 1, we'll use row 2. And then from there, I'm going to just randomly sample the next state, which will either be a 0 or a 1. And the probability of choosing 0 or 1 will be determined by the probability in this row of matrix P. Okay, and so that's going to form, that's going to become the next X value. And then we iterate to the next iteration, and we look at the previous value, and then, you know, we pick the row, and then we select the probability. So that's going to be the Markov chain, right? Does it? I hope that you agree that that looks like the Markov chain. Okay, and again, there's just something, I don't know. For me, it's just kind of fun to watch this thing. Okay, so anyway, so if we do this and we run this 100,000 times, how many zeros and how many ones are we going to get? Okay. Yeah, so in here it's labeled A and B, but we can treat this as a 0 and this is state 1. Okay. So we can say, well, how many times was it equal to 0? And that happened about 75% of the time, 0.7497. And then how many times was it state 1? And that happened about 25% of the time. Okay. All right, so let's try it again, but with a different starting state and a different seed. So this time I'm going to start my state off at state 1. Okay, state 1, and I've got a bunch of NAs. And then we're going to start. I'm going to set the seed different this time. When we use the same code, and then I just let it run, and I say, well, how many times was it state 0? And again, we get something close to 75%, not exactly. How many times was it state 1? And we get something close to 25%, not exactly. But and so, you know, I know we only did 2 examples here, but if you did this multiple times, each with a different starting state and a different seed or whatever, you're gonna get similar results. You're gonna get similar results. Okay, so both of these simulations, and I promise if you did even more of these, you're gonna end up with approximately 75% of the values, 75% of your times you're gonna be in state 0, and around 25% in state 1. Okay, and so we can say, you know, asymptotically in the long run, what is this value going to be? Asymptotically, or in the long run, what is this value going to be? The sum, the proportion that's in state 0 and the proportion that's in state 1. You know, we look at this, what's the proportion in state 0 and the proportion in state 1. You know, based on our simulations, we might guess, okay, that it should be 0.75 and 0.25. But, you know, kind of mathematically, how can we arrive at some value like that? Okay, and so we're going to call pi sub 0 the long run relative frequency that the chain is in state 0, and then pi sub 1 be the long run relative frequency that the chain is at state 1. Okay, and we're going to create a vector pi. The vector pi is the distribution on the state space 0, 1. Okay, so it's going to be kind of the distribution of long run relative frequencies. So, you know, if we keep watching this over and over and over again, in the long run, what proportion of the times is it going to be in state A, and what proportion of the times is it going to be in state B? All right, so this is what we have here. Okay, does so far so good? All right, and so the fraction of the time that that we're in whichever state. So here I just have state 0 and state 1, or state space. There's only 2 values here. But if we had like 3 values, I wonder, can I actually make a 3rd value here? I wonder. I might not be able to. Oh, look at that. Now I got, that's cool. Okay, so anyway, you could have, you can make a, that is cool. I'm so excited. Man, I'm going to do like a 4-way. Okay, so anyway, we could imagine some kind of Markov chain where there's more than 2 states, right? Now we've got a Markov chain with 3 states, and here it's like switching and all sorts of stuff. And so the fraction that a Markov chain spends in some state J, okay, is going to be pi sub j, right? That is, in the long run, what proportion does the Markov chain spend in whatever state we're talking about? That's going to be the value. And so, you know, back on here, we're kind of guessing just based on our trials. It seems like, oh, maybe we should pick 0.75 or something just because it's rounding something around there. So, you know, if pi sub 0 is set 0.75, then the Markov chain is in state 0 around 75% of the time. And the probability that xn is in state j is pi sub j. And this is basically the limit as n goes to infinity. What is the probability that random variable x at time n is equal to 0, okay? And that's going to equal 0.75. That's going to be pi sub 0. Okay, and it's going to be pi sub 0 whether or not the initial state, x at time 0, was that equal to 0, or was x at time 0 equal to 1? The whole point of this is that no matter where you start your Markov chain, whether you started it in state 0 or started it in state 1, where you're going to be way into the future is independent of where you started, okay? So, you know, if you think of the weather as a Markov chain, okay, it doesn't matter what the weather was like on January 1st, okay? Whether January 1st was a sunny day, a cloudy day, or whatever, okay? The weather today doesn't matter there, okay? You know, the weather today, maybe it only really mattered what it was like yesterday, okay? Or the weather tomorrow really only matters on the weather today. That's kind of the idea of this limiting distribution, okay? It's just that kind of in the long run, everything kind of, it becomes independent, okay? All right, and so the distribution is of this kind of whatever state x is in at time n is going to be independent of the initial state, x at time 0. All right. Okay, let me go ahead and give you your first quiz answer for today. First quiz answer for Wednesday is B. B as in boy. B as in boy is your first quiz answer for today. All right, so we've got in general, pi, the limiting distribution, is going to be pi sub 0, pi sub 1, pi sub 2, all the way up through pi sub n, is a probability distribution on the state space 0 through n. Okay, so if you've got n different possible states, pi 0 through pi n is going to be the probability distribution on 0 through n. Okay, and we're going to say that pi is the limiting distribution of the Markov chain if this notion is true, that x at time n at state j, x at time n is equal to j, so this is going to be pi sub j, no matter what state we were in the initial step, x at time 0. Okay, x at time 0, no matter what our initial state was in, eventually at some point, okay, some point in the future, it's going to just be pi sub j. Okay, it doesn't matter what our initial state was. All right, and so if this, okay, and this limiting distribution doesn't always exist, okay, but if it does exist, all right, then this pi sub j, okay, represents the probability that x at time n is in state j, independent of the initial state x0, and then it's also the going to just be the long run expected fraction of the time that the Markov chain spends in state j. All right, hang on, give me a second here. Okay, all right, and the stationary distribution. Okay, so we've been talking about limiting distribution. The stationary distribution is the distribution over states so that the expected distribution of the Markov chain at the next step is the same as the stationary distribution, okay? So the stationary distribution is going to be the distribution of the system at equilibrium. If it's at equilibrium, things might still be moving around, but everything's kind of balancing each other out, so that if you are at the stationary distribution at this current step, we're expecting you to be at the stationary distribution at the next step as well, okay? And so if the limiting distribution of a Markov chain does exist, it's going to be the stationary distribution. There's kind of and there's a theorem that says if a Markov chain is ergodic, it will eventually converge to a stationary distribution. Okay, just that if the Markov chain is has this property of being ergodic, and we'll talk about what that means, then in the long run, you could start the Markov chain at kind of any one of these states, and it will eventually reach its limiting distribution, and the limiting distribution is going to be the stationary distribution. So, I'm going to talk about give you some definitions about what it means to be ergodic, and we'll give you some definitions here. These are mostly informal definitions. You can go down a big rabbit hole on stochastic processes, and you can just look up ergodicity, okay, and ergodic theory, and there's a lot of stuff that you can read up on in Wikipedia, okay, and these are going to be a lot more mathematically formal and rigorous. I'm just kind of giving you the general gist of the ideas of these things, okay? All right, so we're going to say a Markov chain is ergodic if we can start the state at any state I. So whatever your state space is, we can start it at any spot. And then at some time in the future, okay, it could be in the distant future, but at some time in the future, it didn't matter where you started, but now it's going to reach kind of this point of equilibrium, right? So you could start with it's kind of just like if you've got the water, like a cup of water, and you could put a drop of food coloring on one edge of the tank or on the other edge of the tank, and just given enough time, eventually that food coloring is going to disperse through the entire tank, right? There's kind of, if you think of each droplet, each molecule of food coloring behaving like kind of Brownian motion, which is like a Markov chain itself, eventually the whole kind of tank is going to, the food coloring is going to disperse, right? And it doesn't matter where you put it, okay? So it doesn't matter what your initial state is, at some time in the future, it's going to kind of spread out, okay? And what we're trying to say is that at some time in the future, the probability of being in any of the other states, okay, is going to be greater than 0, okay? So it's going to be ergodic as long as there's a non-zero probability for all of the other states, okay? Some of the states might have a very low probability, but as long as it's greater than 0, then we're okay, okay? And this has to be true for some finite integer. So we can't just say it's going to happen off in infinity. It's got to be true for some value less than infinity, right? So it's got to happen eventually, okay? Now a finite integer could be a really, really, really big number, just not infinity, okay? And so for a Markov chain to be ergodic, it has to meet these two criteria. It's got to be irreducible, and it's got to be aperiodic. Okay, so now I'm going to have to define what these things are for you. Okay, all right, and this, again, this is the more informal definition, okay? All right, so a Markov chain is irreducible if all the states communicate with each other, okay? And if it's not, a Markov chain is reducible if it's not irreducible. Okay, so we're going to say two states I and j communicate with each other if there's a path that goes from I to J, and there's a path that goes from J to I, okay? And so here, we can look at state 0 and state 3, and there's not like a direct path, but you can go from state 0 to state 1 to state 2 and get to state 3. So there is a way to reach state 3 from state 0, okay? So from 0, you can reach state 3. You have to go through 1 and 2 first, but you can reach state 3. And then from state 3, can you get to state 0? Yes, you have to go through 2 and then through 1, but you can also get through state 0. You can also get to state 0, okay? And if you look at all 4 of these states, or all 5 of these states, all of the states communicate with each other, okay? 4 can talk to 3, can reach to 2, can reach to 1, can reach to 0, can reach to 1, 2, 3, and 4. So, right? All of these, you can kind of, no matter where you are, if I say, so you start here and you need to end up over here, you can do it, okay? So all the states communicate with each other. If you start at any of the states, there is a path, there is a way to get to all of the other states. So this is an irreducible chain. Okay. On the other hand, this Markov chain is reducible, okay? The states do not communicate with, all of the states do not communicate with each other, right? I've removed an important kind of link here. And so if you start at state 0, 1, or 2, there's no way for you to get to state 3 or 4, right? So if you start at 0, you can get to state 1, state 2, but from state 2, you can only go back to state 1 or state and state 0, okay? There's no way for you to go from state 2 into state 3 or into state 4, okay? If you're at 3 or 4, from state 3, you can reach 4. You can also reach 2, 1, and 0. And from 4, you can reach state 3, 2, 1, and 0. So we would say, you know, states 3 and 4 have access to 0, 1, and 2, but states 0, 1, and 2 do not have access to states 3 and 4, okay? And so we would call this is a reducible chain, okay? This Markov chain is reducible because all the states don't communicate with each other. And we might say it's reducible because if you have a chain that starts at states 0, 1, or 2, okay, then this diagram of the chain can be reduced to just those 3 states, okay? There's no point. If you have a chain that starts off at 0, 1, and 2, there's no point including really states 3 and 4 into your diagram because the resulting Markov chain is just going to be a result. It's just going to have these 3 states in it, right? So you can reduce, you know, kind of your diagram there. All right, is that all right for reducible chains? Okay, if state connected to 4, yeah, if we had an arrow that went from state 2 to state 4, then it would become irreducible. Because if we had an arrow that went from state 2 to state 4, then from state 2, we can reach all of the other states, right? We can go from 2 to 4 and then to 3, okay? So we can go from 2 to 4 and then to 3. But if we had an arrow that went to 4, but then we got rid of this arrow, then it would become reducible because basically state 4 becomes kind of an absorbing state. Once it reaches 4, it's done. The chain is over. So you have stuff like that, okay? But well, actually, you would need from state 4, you would need to have one arrow, maybe an arrow back to itself or something. But yeah, right now, so this is reducible. But if you have an arrow that goes from 2 to 3 or 2 to 4, then it becomes irreducible again. Okay, so is that okay? The idea of reducible versus irreducible? All right, there's another concept, and this is the period of a state, okay? The period of a state is the greatest common divisor of n, okay? Which is the number of steps you can take and end up back at kind of your starting state, okay? So like how many steps can you take and still end up back at where you began, okay? So we're gonna just look at, let's say, look at state 3, okay? And you know, there's lots of different pathways we can take to end up back at state 3, okay? So we can go from 3 to 2, back to 3. Okay, so that's 2 steps to 2, 1, 2. So okay, and then we end up back at state 3. Okay, I can go from 3 to 4 to 3 to 2 to 3, and that would be 4 steps. Okay, and you are allowed to visit the same state or your own state before ending at the state. Okay, that's allowed. So this is 1, 2, 3, 4. Okay, that's 4 steps. You can go 3 to 2 to 1 to 2 to 3. That's also 4 steps. Again, 3 to 2 is 1, 2 to 1 is 2, 1 to 2 is 3, and 2 to 3 is 4. Okay, 4 steps. Or you can go 3, 2, 1, start at 3, 2, 1, 0, 1, 2, 3, and that would be 6 steps. Okay, and so on and so forth. Okay, and if you go and you count up how many different steps it takes, how many steps you can take and still end up back at state 3, you're going to find that they're all going to be multiples of 2, right? You got 2, 4, 6, 8, so on and so forth. And the greatest common divisor among all of those numbers is 2. So state 3 has a period of 2. Okay, so state 3 has a period of 2. I wonder, here, I'm curious what this is. So I'm going to try, I'm going to put in a 1 here. So here I'm going to make a Markov chain with a, I want to do 1, zeros everywhere. It's running around on me. Okay, here we go. Okay, so here, if you're at A, you have to go to B. If you're at B, you have to go to C, and C, you have to go to A. All right, so this has a period of 3. Okay, to start at A and end up back at A, it takes 1, 2, 3, 3 steps. And then this, you know, to start at B and end up back at B, it takes 3. So this state A has a period of 3. Okay, this has a period of 3. Okay, so you know that's I don't know how to. Okay, so anyway, but this one, but this is irreducible, right? Because whatever state you start in, it's possible to reach all of the other states. Okay, I'm not sure why it's bouncing around, but anyway. Okay, so anyway, this has a state, state 3 has a period of 2, and so on and so forth. Okay, so that's going to be the period. If I add a pathway for a state 4 to repeat and return to itself, let's look at state 3 again, okay? How many steps can we take and end up back at itself, right? So we can go to 3 to 4 to 3, and that's 2 steps, okay? I can go to 3 to 4, and from 4 back to 4, back to 3, okay? And that's 3 steps, so that's 1, 2, 3, okay? I can also go 3, 2, 1, 2, 3. So that's 1, 2, 3, 4. That's allowed. And I can just also go 3 to 4 and just loop around a whole bunch of times. I can go 1, 2, 3, 4, back to 3, 5. Okay. And so, you know, the greatest common divisor among all of these steps, whether it's 2, 3, 4, or 5 steps, is 1. So state 3 now has a period of 1. Okay. And if you look at any of the other states, we can kind of take advantage of the fact that 4 goes back to itself, and we can visit. If you say, well, I want you to get back, start at state 2 and end up back at state 2 at some, you can pick a random number, you know, 75, and we could figure it out, right? We can just take advantage of, like, go back to 4 a whole bunch of times and end up back at number 2. And so, so all of these, if you look at all of them, you'll see all of the states will have a period of 1, okay? So to end up back at state 0, you know, maybe it's got to be 2, 4, 6, or 8, but then it can also be 9, 10, or 11, right? So it's either you can get back to state 0 in 2, 4, 6, 8, 9, 10, 11, 12, 13, 14, something like that. And so if you look at any of the states, you're going to find that all of them have a period of 1, okay? It's just the greatest common divisor of kind of all of the different ends that exist, okay? Whereas in some cases, depending on the structure of the chain, you're going to have this, okay? But as soon as what we're going to find, oops, as soon as I make one of the chains able to kind of go back to itself, all right, what I want to do, okay? So as soon as the chain can kind of go back to itself sometimes, let's reduce this here, right here. I don't know why why this chain just wants to dance around the screen, but anyway, you can see now that it can kind of end up going back here. You know, how many steps does it take to go from step A to back to step A? And it can be kind of any integer now. It doesn't have to be 3. It can be 4. It can be 5. It can be 6. It can, you know, anything larger than 3, basically. Okay, so a Markov chain is going to be aperiodic if all the states have a period of 1. Okay, and so one way to get an aperiodic chain, if you just want to know, is it aperiodic, you can see if it's irreducible, meaning all the states can reach each other, and at least one of the states is able to go back to itself, then the chain is going to be aperiodic. Okay, so as soon as you make one of the chain states able to go back to itself, then it'll be aperiodic. Now, technically, this is not this is not the only condition, right? So you can have an aperiodic chain where you don't have a state go back to itself. Okay, you can set up a structure, but that's kind of a simple structure that will make a chain aperiodic. And this condition that a chain can go back to itself is fine. Okay. All right. So let's revisit this kind of two-state business here. Let me go back to. Well, okay. So this is what we had here. All right. Okay, so we're going to revisit our two-state Markov chain, and we want to see, okay, where can we achieve equilibrium? Okay, we want to say the probability of transitioning to state 0. Okay, we're going to have equilibrium basically when this arrow, the amount flowing from 0 to 1, is equal to the amount flowing from 1 to 0. Okay, or I should say the probability of flowing from 0 to 1 is equal to the probability of flowing from 1 to 0. So this is, that's when we will achieve equilibrium, and that's when we'll kind of be at our steady state, or our stationary distribution, and that's kind of when we'll reach the limiting distribution there. All right, so let's think about this, okay? So if you're already at state 0, okay, then the probability of going to state 1 is the probability that at the next, so if you're currently at time n, if you're currently at 0, given that you're at state 0, then the probability of being at state 1 in the next iteration is 0.2, okay? And thus the total probability of transitioning from state 0 to state 1 is going to be basically equal to the probability of being at state 0, okay, which for now I'm calling P0, the probability of being at state 0 multiplied by the probability of transitioning to state 1, given that you're at state 0. So we're going to say the probability of being at state 0 multiplied by that transition probability, which is, you know, the top left corner, I'm sorry, top right corner of this matrix. Going from 0 to 1 is this right here, 0.2. All right, and then if you're already at state 1, then the transition probability of going to state 0 is 0.6. Okay, that's P10. That's this value right here in this corner, and that would be if you're currently at state, the state at time n is equal to 1, then what's the probability of being at state 0 in the next iteration? That's going to be 0.6, and therefore the total probability of transitioning to state 1 is going to be the probability, I mean state 0 is the probability of starting off at state 1 and moving to state 0. Okay, so we want to set, we basically want to set this thing equal to this thing, right? That's how we're going to achieve equilibrium. If the amount going from 0 to 1 is equal to the amount flowing from 1 to 0, then we'll achieve kind of equilibrium, and we can kind of expect everything to be the same from there. All right, So, so we want to find a distribution, right? So at the steady state, so instead of calling this P0 and P1, I'm going to call it pi sub 0 and pi sub 1. And we want to find a distribution, pi sub 0 and pi sub 1, that will satisfy this criteria. Okay, so we've got pi 0 times P01 and pi 1 times P10. We want the amount going from 0 to 1 equal to the amount going from 1 to 0. And so that's going to be this value. P01 is 0.2 and P10 is 0.6. Okay, and so we're going to say 0.2 pi 0 and 0.6 pi 1 is going to, they're equal to each other. And there's also the condition, because it's a limiting distribution, that these things have to sum up to 1, right? So pi 0 plus pi 1, those have to equal 1 because we want a distribution over the states. Okay, so if you just kind of divide both sides by pi 1 and both sides by pi 2, you're going to get pi 0 over pi 1 is equal to 3. And then if you solve for that in here, then you're going to get pi 0 equal to 0.75 and pi 1 equal to 0.25. Okay, so if you just kind of solve this and this together, you're going to get pi 0 is equal to 0.75 and pi 1 equal to 0.25. Okay, and we will see that, yes, indeed, this is our stationary distribution. That if I take my stationary distribution of 0.75, 0.25, and I multiply it by the matrix P, the transition matrix P, 0.8, 0.2, 0.6, 0.4, okay, and if I do this, you will see that you will end up getting back the stationary distribution. So 0.75 times 0.8 is 0.6, and 0.25 times 0.6 is 0.15. Okay, so those two add up to 0.75. And then if I take this multiplied by the second column right here and right here, 0.75 times 0.2 is 0.15, and 0.25 times 0.4 is going to be 0.1. Okay, so that evens out to be 0.75, 0.25. And so what we find is that if you've reached the stationary distribution pi, where your values are distributed 0.75, 0.25, then after applying the transition matrix, you will end up back at 0.75, 0.25. Okay, so pi times p is equal to just pi. So we have this property here. Okay, pi times p equal to pi. All right, and so that's going to be the stationary distribution. Oh, let me give you another quiz answer. Second quiz answer tonight for today is D. D as in dog. Okay, second quiz answer is D. D as in dog. All right, and so this structure is, this vector pi is what we call the left eigenvector of the matrix P, okay? So normally when you learned about eigenvectors, it was always kind of in the form of a matrix times a vector is equal to a scalar times a vector. And the vector came on the right-hand side of the matrix, right? It would be matrix multiplied by a vector. So the vector was written on the right-hand side. So this is what's known as a right eigenvector, and that's traditionally what you talk about when you talk about eigenvectors. When you talk about an eigenvector, generally textbooks are referring to the right eigenvector, okay? But this is still technically an eigenvector. It's just called the left eigenvector because the matrix, the vector is put on the left side of the matrix when you do the multiplication, okay? So just with a little bit of linear algebra, you do pi times p, and if you take the transpose of this, okay, then you get the matrix transpose times pi transpose pi transpose. And so you find the left eigenvector, which is a row vector, okay, whereas over here this is a column vector. The left eigenvector of p is equal to the transpose. You're going to get pi transpose, the transpose of the right eigenvector of p transpose. So if you take the right eigenvector of your matrix P transpose, okay, then you're going to get the transpose of basically the left eigenvector. Okay. So we can do that. So I've plugged in our transition matrix. Okay, so again, here's our transition matrix, 0.8, 0.2, 0.6, 0.4. Okay, so here's my transition matrix. And when you use the function eigen in R, that it finds the right eigenvectors. Okay, there's no left eigenvector function. So we just kind of take what we learned, and we're going to just take the transpose of P, and we're going to find the right eigenvectors of P transpose. Okay, the transpose of P. All right, and so these first columns, we get two eigenvectors. Okay, and this first column is the one we're going to keep because it's all positive. We can't have a distribution where one of the probabilities is negative. So this is no good. So we're going to keep this one because its values are all positive. And this is going to be the eigenvector we keep. Okay. And so this is, I'm going to take this and I'm going to take the first column of the eigenvectors, first column here, and I'm going to transpose that. Okay. So the left eigenvector is a row matrix, or I'm sorry, a row vector. And so we're going to take the transpose of this. Okay, and that's going to be my stationary distribution. And to kind of normalize this, I need the sum to equal 1. So I'm going to just take the stationary, this eigenvector, which is 0.9486 and 0.3162. I'm going to take the sum of those and divide each of those by the sum. Okay, because this adds up to something bigger than 1 right now. And so we're going to just normalize them. And then when we do that, we get the same stationary distribution that we found earlier, 0.75 and 0.25. Yeah, I think that's good, right? Okay, and so again, same website. They came up with some really great illustrations here. Ooh, it's a little too big. Here's a good picture. And so here is kind of a two-state Markov chain diagram. Here it says people can go from California to New York, and people can go from New York to California. And here it says each year 10% of Californians will go to New York, and 30% of New Yorkers will go to California. So the transition probabilities are a little bit different from, oh, you can, oh, look at that. You can, oh, let's put in our numbers. Okay, we want 0.6 and 0.2. Oh, this is so exciting. I wasn't able to do this yesterday. Okay, all right. So we're gonna, we want this to be 0.6. Oh, I can't, oh, I had it. Okay, there we go. 0.6, and we want this to be 0.4. Okay, so we're gonna, wait, 0.6 and 0.2, sorry. Oh, there we go. Okay. All right. So, okay. So we've got from California, we're going to say 20% go to New York, and then from New York, we're going to go to California. Okay. And technically, you can start off with any kind of starting distribution here. Okay. So no matter where we start, watch what happens. Okay. We're gonna move 20% of Californians are going to move to New York, and then 60% of New York is going to come to California, okay? And then when you do that, now we've reached equilibrium where the same amount go from California to New York as the amount coming from New York to California, okay? And I can start off with a totally different amount, okay? I can shrink this down like this. We're going to move 20% of California to New York, okay? 20% of New York to California. And then when we do that, now we have reached equilibrium where I don't know if I can slow this down, but the amount going from California to New York is equal to the amount coming from New York to California. And we can, wherever we start this, okay? Okay. So it starts off like this, and eventually we'll reach equilibrium where kind of the same amount goes from California to New York and New York back to California, okay? And this is kind of, so this is the kind of the stationary distribution. What proportion is here and what proportion is over here? We're going to get, it's going to be around 75%, 25% is going to be here. Okay. If I, let me see if I can mess with this and just change, okay. So here we're going to say only 10% of Californians go to New York, but 90% of New Yorkers go to California. Okay, so let's just shrink this down like this. Okay, and let's just see what happens. So we're bringing 90% of New Yorkers back to California, and then here we can see basically around. Okay, just because it's a finite number and we can't. We get basically 5 or 6 going over at a time, and then 5 or 6 coming back over here, just because of kind of rounding issues as far as whole numbers go. Maybe if I tweak this a little bit. Okay, so at some steady state distribution here, we get 5 people coming from California to New York, and 5 people going from New York to California, right? And so at this point, we have reached kind of this equilibrium here. So anyway, these things I think are pretty cool at illustrating kind of this concept of reaching the stationary distribution, where at some point, okay, so in the beginning, the populations change drastically, but then after a while, okay, the amounts equalize, okay. And this is over here to kind of show, you know, what you can kind of start off with the population of California and the population of New York. You can kind of start it off at different things, and eventually it plots out at, you know, kind of the relative proportions of California and New York. And what we see is that the values in this diagram show up where it's going to align with whatever the eigenvector is. Okay, so you can kind of mess around with this, and if you change these this amount here, this is actually not going to, we'll get it will change kind of where the location of the steady state is. All right, so anyway, you should play around with this. It's kind of fun. I mean, I'm into this kind of stuff. So, oh, okay. Before we end for today, okay. So what we saw today is that if you got an ergodic Markov chain with some transition matrix P, it's going to have a stationary distribution pi, okay? And what we see is that if we let this chain run long enough, it's going to eventually converge to a stationary distribution. And kind of from that point on, once you reach the stationary distribution, the values that it generates will come from the stationary distribution. And so the next idea that we want is we want to know, let's say there's some target probability distribution that we want to generate values from, right? So we want to be able to generate samples from some target distribution. And the question now is, can we design a Markov chain? Okay, that is, can we figure out what transition probabilities to use so that the stationary distribution of the Markov chain is going to equal the target distribution, right? Because we know eventually an ergodic Markov chain is going to generate values from a stationary distribution, right? You let it run long enough, it's going to converge to the stationary distribution. And so can we design the thing so that the stationary distribution is equal to the target distribution? Okay. And can we figure out what? Yeah, I think I've lost my train of thought when I was writing this, but yeah, that's what we want to do, and we're going to start exploring that with the Metropolis-Hastings algorithm, I guess we'll start off with the Metropolis algorithm, and then we'll generalize to the Metropolis-Hastings. So okay, anyway, sorry for going a couple minutes over, but that's what we've got for today, and we will see you guys on Friday.